Hello, my name is Kaya Brown. This is Lab 5 for Physics 2212, Magnetic Bracking with Faraday's Law. So we have our table of contents. First, we have our introduction. This includes all of our key concepts and key equations that we'll need for this experiment. Choose the experiment itself with the procedures and results. And then we also have the computational model made in GlowScript, of course. And then we have our conclusion that answers our discussion questions. So the introduction, formulas, and our key ideas. So just to begin with this lab, we're going to observe Faraday's law using a bar magnet falling through an aluminum non-ferrous tube. That's a really important part. So we're going to model this phenomenon both computationally with GlowScript and a real-life model using just an aluminum tube and then our bar magnet and then our magnetometer, which is on our phone. So our key concepts today include Faraday's law, calculation of magnetic field using the Boix-Savart law, Ohm's law, magnetic force formula, interaction between currents and magnets, Lenz's law, and then also the time derivative flux on a dipole. So here are all of our formulas written out, and these are essentially what we're going to do for calculations in our computational model. So introduction to lab, as I said before, we're just going to use this tube and we're going to essentially first find magnetic north with our magnetometer. This is very important. And then we're going to go ahead and drop our bar magnet, and then we're going to record ourselves dropping this bar magnet down the tube. And then we're going to see how much time it takes for the bar magnet to exit the tube. And we're going to do this 5 times and get the average value of this. So our assumptions is that we can ignore any of the forces that are not gravitational or magnetic forces. So that means we'll ignore the friction force. So systems and surrounding, the system includes the aluminum tube and the magnetic bar, whereas the surrounding is everything else that isn't that. So here are our measurements and results. For the length of the tube, we have our radius of the tube. Then we also have our mu value, which has been slightly adjusted to 4.5 am squared. We have our width, which is 0.00 meters, which is always need to be in like our standard units of meters and kilograms. This is very important for the experiment. And then we also have our magnet mass as 0.03 kilograms. And then we have our times here. So we ended up with an average time of 1.252 seconds. So this is just an average of all of the trials that we did. So here are our checkpoint questions. Why can't we use a ferrous tube, for example, or a steel pipe? Essentially because there are magnetic materials in ferrous, there are magnetic properties in ferrous materials that would have essentially interfered with the movement of magnetic bar. Then what happens to the magnet, and how does it compare to a magnet falling in free space without a tube? So we even saw this in class that the magnet would fall at a much slower speed just due to the magnetic field just kind of halting the velocity of the magnetic bar. So it moves slower than it would in free space. So here's our computational model. So first we establish our physical concepts, and then we also set up the graph, which is going to plot the velocity versus the time, which we'll see in a second. So then we also have created the tube of the aluminum foil. So it's like a pretty accurate model. We have the tube here and everything such as that. And then we also have a bar magnet that we created, and then the initial conditions of the bar magnet. And then we also made sure to calculate the magnetic flux using the equation seen before. And then we have our simulation loop just to repeatedly see the magnet falling through the bar, as well as the magnetic current. So we have both of the currents that are flowing in the counterclockwise and clockwise direction. This is just to simulate the current that would be occurring in real life so we could have a visual. And here's our velocity versus time graph. As you can see, it goes down and it plateaus. So we have our checkpoint question. So our first one, essentially the blue is the clockwise back in our simulation, and the red is the counterclockwise. You can essentially use as Lenz's law to find this. And then we also have what happens to the dynamic of the system when you flip the magnet around. The direction of the current would change, but nothing else would. So the computational model and then our real world model are very similar. There's a little difference, but the computational model could be altered a bit to account for things that we just assumed as assumptions. So we also have what if the shape of the velocity? So we see that earlier there's a plateau of the graph, and then we also see that there's a steep downwards, which shows that there's differences in velocity and then the differences of the forces that are influencing. So we have like our results, and then physics errors. We had some that might have been related to timing or small errors with the aluminum tubing. And then our questions, we have what if resistivity was reduced? So essentially that would be the magnetic force would be way stronger according to Ohm's law. Since there would be no resistivity, it would just be a way stronger current. And then if holes were cut in the tube, how would this affect the magnetic current rings in your model? There'd be less current and the magnet would move way faster. All right, thank you guys for watching. That's it.